Another important concept about probabilities is the concept of conditional probability and independence. For conditional probability, it looks at two events again, and here it's called conditional because it computes or it refers to the probability of an event A given that another event or event B has occurred already. So it refers to the probability of an event happening given or provided that another event already happened in the first place. And again, we call that the conditional probability of A given B. And this is how we denote conditional probabilities. That's P, and then inside the parentheses are two events, A and B, separated by a straight line. And we read this normally as the probability or P of A given B, or the probability that event A will occur given that B already happened. So in this example, we can find multiple conditional probabilities. Let's say you have 100 students, 70 of those students enrolled in a review center, and 35 of those who enrolled in the review center got accepted into the Ateneo de Manila University. So one possible conditional probability is the probability that one of the 100 students was accepted into Ateneo given that the student enrolled in a review center. So again, we can compute for the probability of a randomly selected student out of the 100 being accepted into Ateneo, knowing that that particular student has enrolled in the review center. So that's one possible conditional probability in this example. Now, to compute for probabilities, for conditional probabilities, we have this general formula. So the probability of A given B is equal to the probability of the intersection of the two events A and B divided by the probability of B, where P of B is greater than 0. So this one should be greater than 0 so that the probability is not undefined. Now, this is also the general formula for this conditional probability, wherein the order of the letters is different. So again, because conditional probability assumes that one event has already occurred, switching or changing the order of the events gives an entirely different probability. So P of B given A is different from P of A given B, but in terms of the formula, it follows the general pattern of the first one. So if you look at the first formula, when computing for the conditional probability of A given B, the numerator is just the intersection of those two events, while the denominator is the probability of the event to the right of the line, which is P of B. So that is the same pattern that we will use when computing for P of B given A. So the numerator is still the intersection of A and B, but the denominator is now P of A, because A is now the one at the right of the line, making that now the denominator. So using that general pattern, we can compute for probabilities of the conditional probability of an event given that another event already happened. So again, here are possible interpretations. So we can say that we are restricting the sample space. Instead of looking at all the possible outcomes, we are restricting the sample space to only those outcomes where B already occurred. So again, the conditional probability is the chance that A will occur given this new sample space, given that B happened in those remaining outcomes. Or in other words, if B occurred, what is now the chance that A will also occur? Now, from the two formulas we got earlier, we can get formulas to compute for the intersection of events A and B. So using one of the two formulas, we can cross multiply and get the formula for the intersection of A and B, which is the product of P of A and the probability of B given A. Or another way to compute for the intersection of events A and B is by multiplying P of B to P of A given B. And again, both of these equations come from these two formulas. So when you cross multiply, you'll get two ways to compute for the probability of the intersection of those two events. Here's an example that will allow us to see how to determine probabilities and how to compute for missing probabilities. So the Best Review Center claims that if you enroll for your college entrance test reviews there, the probability of getting accepted into the Ateneo is 70%. Historically, only 5% of all asset takers enroll at the Best Review Center. Now, assuming that their claim is true, what is the probability that a randomly selected asset taker enrolled in the review center and got accepted at the same time? So when answering these kinds of problems, the first step is to identify the present events first. Or you can also start by breaking it down further into the experiment, the experimental outcomes, the sample space, and the events. So in this example, our experiment involves randomly selecting a student. So that's the experiment. And then the outcomes of that experiment are the different students. Now, some of the students have taken the asset, some of them were accepted, some of them enrolled in the Best Review Center. So those are the relevant events in this experiment. So among all the possible sets of outcomes in the sample space, we will focus only on two events. First is when it refers to the event where the randomly selected asset taker got accepted into the Ateneo, and another event wherein the randomly selected student enrolled at the Best Review Center. So we can let A be the event where a student got accepted, or B be the event where a student enrolled in the Best Review Center. Now, given these representations, we can now start identifying the probabilities. So in the problem, some percentages or proportions or probabilities were given, and now we have to identify what these probabilities represent or imply. So again, 70% is the probability of getting accepted into the Ateneo if the student enrolled in the Best Review Center. So the word if should be a clue. Because of the word if, it signifies that this probability is a conditional probability, and given this representation, 70% is P of A given B. Or again, the probability that the student got accepted given that the same student enrolled in the Best Review Center. And again, that's 70%. Now, another probability was given earlier, and that was 5%. And this refers to the proportion of the asset takers who enroll at the Best Review Center. So 5% is also another probability, and that is the probability of B. So P of B is known to be 0.05, and the problem is asking for the probability that a randomly selected asset taker enrolled and got accepted at the same time. So the clue here is the word "and". This represents the intersection of events, and particularly, this problem is asking for the probability of the intersection of A and B. So to compute for the intersection, we can use two formulas. Remember, there are two ways to compute for intersections. We can get the product of P of A and P of B given A, or the product of P of B and P of A given B. Now, between these two formulas, we can only use the second one because we don't know P of A and we also don't know P of B given A. But here in this formula, both are given, so we can use this to compute for this probability. So that's 0.05 times 0.70 or 0.035 or 3.5%. And to interpret this probability, since this is the probability of the intersection of A and B, this means that if we randomly select one asset taker, the probability that the randomly selected student got accepted and enrolled at the best review center at the same time is 3.5% only. Now, in this example, to celebrate their anniversary in the Philippines, an international brand of donuts offered a special promo for one day only, which was advertised through social media. Out of 60 randomly selected customers who were lined up in their biggest branch in the country, 54 availed the promo, and 52 of those who availed the promo saw the advertisement online. Also, 55 out of the 60 saw the advertisement online. What is the probability that a randomly selected customer availed the promo given that he or she saw the advertisement? So our approach here again is to identify the experiment, the experimental outcomes, the sample space, and the relevant events, and then define those events. So in this example, our experiment involves randomly selecting a customer out of the 60 who lined up. So that's your experiment. And the possible outcomes of that experiment are all those 60 people who lined up. Now, among all those 60, there are some similarities. Some of them availed the promo, some of them did not. Some of them saw the advertisement online, while some of them did not. So, among all the possible categories or all the possible events or sets of outcomes, the two clear events that we are looking at in this example are the seeing the advertisement and availing the promo. So we can label these two events using letters, or you can also use words to represent the events. So we can let the word availed represent the event where the customer availed the promo, and the word saw to represent the event where the customer saw the advertisement. Now, after identifying the events, you can now start looking for those probabilities. So the total is 60, and we have here some information. We have 54, 52, and then 55. And from these three values, we can just divide them by 60 to get the probabilities. But aside from knowing that these are probabilities, we also have to be careful in how we represent those probabilities. For example, 54 over 60 is a probability, but how do we denote that probability? The similarity of all the 54 out of the 60 is that all of them availed the promo. Therefore, 54 over 60 is the probability of avail, and this is also equal to 90%. Now, we had another value earlier, which is 52, and the similarity between all these 52 customers out of the 60 is that they availed the promo and they also saw the advertisement online. So these 52 people are part of two events. So we can represent this as the intersection of two events. So the intersection of events A and B, of events availed and saw should be 52 over 60. And then we also have another value here, that's 55, representing those who saw the advertisement online out of the 60, making 55 over 60 the probability of seeing the advertisement. So summarizing all these probabilities that we have identified, we have the following. So P of availed is 0.9. The probability of the intersection of availed and saw is 52 over 60 or 0.8667. And the probability of saw is 55 over 60 or 0.9167. As much as possible, use the exact values, especially if you are still going to use these values in a further computation. Now, the problem is asking for the probability that a randomly selected customer availed the promo given that he or she saw the advertisement. So the word given gives us a clue that the problem is asking for a conditional probability. But between the two possible conditional probabilities, this problem is asking specifically for the probability of availed given so. So we write that as P of availed given so. And to compute for this probability, we'll just have to use the formula that we discussed earlier. So for conditional probabilities, the numerator will always be the intersection of the two events, and the denominator is the probability of the one at the right of the line, which is P of so. Now these two probabilities are given, so that's 0.8667 over 0.9167, or for a more precise computation, that should be 52 over 60 over 55 over 60. And that will give us 52 over 55, or approximately 0.9455, which means that if you randomly select one customer who is in line, if you know that that particular customer saw the advertisement online, there is a 94.55% chance that the same customer availed the promo. Now we have another concept called independence of events, and this talks about two events again. And if two events are said to be independent, it means that they do not influence or they do not affect each other. Meaning, even if A occurs or not, it does not affect the occurrence of B, and vice versa. So the two events do not influence each other, they don't affect each other. And to determine if events A and B are independent, we can check using these two equations. If P of A given B is equal to P of A, and if P of B given A is equal to P of B, then we can say that events A and B are independent. Now, what's the logic behind these two equations? Again, P of A given B is the probability that A will happen given that B happened. And if this conditional probability is just equal to P of A, it means that even if you know the occurrence of B, the probability of A is just the same as the probability of A, even if you don't know if B happened or not. And that's the same here. So that's again the concept of independence, and this is how we test mathematically if events A and B are independent. So in this example, your friend has been absent in your school's basketball games for the past few years, but decided to watch again last season. He was present in the first game of the last season and the team won, which motivated him to watch religiously again. However, the team lost consecutively in the next 4 games. He stopped watching after that because his friends were teasing him as bad luck to the team. Given that the team won only 3 out of 15 games last season, is there enough basis to discourage him from watching for the succeeding seasons? So again, you can start by identifying the experiment, the outcomes, the sample space, and the relevant events. So here, your experiment involves randomly selecting one game out of the 15 games last season. And the sample space includes all those 15 games. So all those 15 games are members of the sample space. So each game is an experimental outcome. Now, among all the 15 games, some of them were watched by your friend, some of them were not watched. In some of them, the team won. In some of them, the team did not win. In some of them, they were held in a certain venue, and in some of them, the games were held in another venue. So among all the possible sets of outcomes within the sample space, the two relevant events here in this problem are watching the game and if the team won in that particular game. So the problem is asking for the concept of independence. It's asking if there is basis to discourage him, or in other words, we have to determine if watching is independent from the result of the game so that we can answer this question. So we can let the word watched represent the event wherein your friend watched the game, and then one represent the event wherein the team won the game. And we can identify some probabilities given in the problem. First, we know that your friend watched the first game, and the team won in that game, and then your friend watched the next 4 games. However, the team lost in those next 4 games. After that, your friend stopped watching, so we can get here the total number of times where your friend watched, and that is 5 out of the 15 games. And that becomes the probability of watched, which is 5 over 15 or 1 over 3 or 0.3333. Now we can also get here the probability that the team will win in a randomly selected game. So out of all the 15 games, the team won only 3 times. So the probability of 1 must be 3 over 15 or 0.2. Now we can also get the probability of the intersection of the two. So among all the 15 games, there was only 1 game wherein your friend watched and the team won at the same time, making the probability of the intersection of these two events equal to 1 over 15 or 0.0667. Now to determine if these two events are independent, again, we have to check using the equation shown earlier. So first, P of watched given 1 should be equal to P of watched. Because again, if these two are equal, it means that even if the team won or not, even if you know that the team won in a particular game, the probability of watched is the same as the probability of watched even if you didn't know if the team won the game or not. So to check for independence, we'll just have to compute for this probability and compare that to the probability of watched. So this is conditional probability. So to compute for this probability, we use the same formula. That's the probability of the intersection of watched and 1 over the probability of 1. Probability of watched intersecting with 1 is 1 over 15, while the probability of 1 is 3 over 15. So getting the quotient of the two, we will get 1 over 3, and that's the same as P of watched, which means that these two equations are equal, implying that events watched and 1 are independent, or they don't influence or they don't affect each other. So because of this, because we've shown that these two probabilities are the same, it's enough for us to say that the two are independent. Now, you can also show independence using the other equation. Instead of computing for watched given 1, you can compute for P of 1 given watched and then compare that to the probability of 1. And here, the probability of 1 given watched is computed by, again, dividing the probability of the intersection of the two by the probability of watched. That's the one at the right of the line. So these two probabilities are known. That's 1 over 15 over 5 over 15 or 1 over 5 or 0.2, which is again equal to P of 1, saying that or implying that these two events are independent of each other. Meaning, whether your friend watches or not, it will not affect the chances that the team will win in a particular game. So it's not enough basis for you to discourage your friend from watching the next games if your goal is for your team to win. Here in our last example, we have a local telecommunications company that conducted a study on their subscribers to see if service disruptions significantly affect their subscriber dropout rate. From a sample of 40 respondents, they found out that 34 of them switched ISPs or internet service providers, with 31 of them saying that their main reason for switching is the frequent service disruption that they experienced. A previous study they've done showed that 82% of their customers experienced frequent service disruptions. So we want to know if there is evidence to say that service disruptions affect subscriber dropout. Or in other words, we want to know if these two events are independent or not. So again, we identify or we label these two events. So we can let switch represent the event wherein the subscriber switched to another internet service provider or ISP. And the other event is the event disrupted, which refers to the event wherein the subscriber experienced frequent service disruptions. After identifying the events, our next step is to identify the probabilities. So your sample space is composed of 40 respondents. 34 of them switched out of the 40. So 34 over 40 is a probability, and that is the probability of switched. Now, among the 34, 31 of them switched because of frequent service disruptions, meaning these 31 experienced switching and frequent service disruptions at the same time. So 31 is part of two groups or two events. Therefore, if you divide 31 by 40, you will get the probability of the intersection of the two events. That's 31 over 40 or 0.775. And then finally, 0.82 is the proportion of those who experienced frequent service disruptions. So again, that's P of disrupted or 0.82. Now, to check for independence, again, we'll just have to check any of the two equations. So for the first equation that we can check, that switched given disrupted should be equal to P of switched. So compute for this probability using the same formula, that's the intersection of the two over P of disrupted. So that's 31 over 40 over 0.82, and that will give us a probability of 0.9451, which is greater than P of switched, which is 85%. And from here, we can already say that the two events are not independent. So we can also interpret this probability. 94.51% is the probability that a customer switched given that the customer experienced frequent service disruptions. Or in other words, if you know that a randomly selected customer and experienced frequent service disruptions, there is a higher chance that the same customer switched ISPs. Now, another way to check for independence is through the second equation. So we can check P of disrupted given P of switched, and we will compare that to P of disrupted. So computing for this conditional probability, we'll just again divide the probability of their intersection by P of switched. So that's 0.775 over 0.85 or 0.9118. And again, this is greater than 0.82, which means that these two events are not independent. So again, these two events affect each other, or it means that if you randomly select one customer out of the 40 and you know that that customer switched ISPs, then the probability that the same customer experienced frequent service disruptions in the past is 91.18%, which is higher than the probability that one randomly selected customer experienced frequent service disruptions. And here again, we don't know about the occurrence of the other event, which makes this different from a conditional probability. So you can use just this one or you can use just the first one, and both should be able to tell you the same conclusion, wherein the events are either independent or not independent. Now, the multiplication rule, again, is an equation that allows us to compute for the probability of the intersection of two events. Earlier, we said that the probability of the intersection of A and B can be computed using two approaches, either getting the product of P of A and P of B given A, or the product of P of B and P of A given B. However, if you know that events A and B are independent, it means that P of B given A should be equal to P of B, while P of A given B should be equal to P of A. So in other words, if events A and B are independent, then we can simplify these two equations. So this will be equal to P of B, making the formula just P of A times P of B. Or in this formula, P of A given B will be equal to P of A. Therefore, the simpler formula is just P of A times P of B. So this simplified formula allows us to compute for the intersection of events A and B only if A and B are known to be independent events. Otherwise, if the events are not independent, we have to use the original formulas, either this one or this one, in order to compute for the probability of the intersection of two events.